The content in this video comes from pages 46 through 54 of your textbook, and it's meant to help you achieve learning objective number 6, which is to explain what causes the sun angle and length of daylight to change throughout the year, and to describe how those changes result in seasonal changes in temperature. In a moment, I'll ask you to pause the video and complete a very brief assignment. If you haven't already done it, like I usually say, it would be a good idea to skim the pages listed here before you watch the rest of the video. Paying particular attention to the bold words in the textbook, and those should help, those will include the key terms, and also to the figures in their captions. Now, a lot of these figures can be pretty darn confusing, and so what I hope this video does is take some of that confusion away. Once you start really thinking about these physical relationships between the Earth and the Sun, they start to seem a little bit more logical. But I remember my first time through not really having that be the case until I'd practiced with it a little bit. But please plan to read this content carefully before you take any quizzes associated with the material. We will talk about some of the little questions that come up along the way in class, and maybe you'll see me open a web discussion for some of them. Earth has two principal motions, rotation and revolution. And so in this class, it matters that you know the difference between the two. So rotation is the spinning of Earth on its axis that takes 24 hours, one day, and produces the daily cycle of daylight and nighttime. The other motion, revolution, refers to Earth's movement in a slightly elliptical, not a circular one, but an elliptical orbit around the sun. And that takes about 365.25 days, which is the length of an Earth year. When you geometrically define an ellipse, it's different from a circle in that the circle has a point in the very center of it from which you describe the radius. Right? An ellipse has two centers that are right next to each other, and you can determine two radii for that ellipse. They should be about the same in a balanced ellipse like we have around the Earth, but notice that the sun is located on only one of those elliptical centers. And because the Earth isn't circular, the distance between the Earth and the sun varies during a year. So each year, on about January 3rd, our planet is 147 million kilometers away from the sun. Closer than at any other time in the year. That's a position called perihelion. Notice that January 3rd isn't exactly the first day of winter, but it's 12 days after or so. When we talk about seasons, which is in this presentation, it's important to realize that there's no connection between the timing of perihelion and the seasons on Earth. So in other words, we could at some point in the distant future, and probably have at some point in the distant past, seen a bunch of different dates for perihelion. But about 6 months after perihelion, this is July 4th, Earth is 152 million kilometers away from the sun, and farther away than any other time in the Earth's orbit. This is a position called aphelion. Okay, so the helion refers to the sun. A means away, and peri means close. So although the Earth is closest to the sun and receives as much as 7% more energy in January than in July, the difference plays only a minor role in producing the seasonal temperature variations. Okay, so this is not the cause of a season. Not Earth seasons are not caused by this, but it is an important physical factor for understanding climate and climate change. So when we are closest to the sun, that's the northern hemisphere's winter. When we are furthest away, that's the northern hemisphere's summer. As the Earth revolves around the sun, it's tilted on its axis by an angle of about 23.5 degrees. Okay, that's illustrated in this figure right here. So when we look at that angle, that's a very important one for our seasonality. We think that angle occurred when Earth collided, or a meteor collided with Earth, and probably the same one that made our moon. The moon is a chunk of the Earth that got blasted off, and not in such a great distance that it escaped our orbit. So it's drawn to the Earth, just like we are drawn to the sun. You'll notice in this figure, though, that the Earth's axis always points to the same general area in space. Okay, so there's no flopping back and forth. We always see it pointing towards the North Star. And in June, when the northern hemisphere tips towards the sun, more direct sunlight and long hours of daylight cause warmer weather than in December on the left-hand side of this picture. So in December, the northern hemisphere is tipped away from the sun, and you see the southern hemisphere is tipped toward the sun. That's why we have the opposite seasons in the northern hemisphere from those that are experienced in the southern hemisphere. So it also explains something about the angle of sunlight. So we know this isn't a scaled drawing. This is very simplified, and the distance between the Earth and the sun would be much bigger, wouldn't fit on this slide if we drew this to scale. If the sun were this big, the Earth shouldn't be this big, it should be much smaller. And the diagram would take up much more space than we have here. So it's a scaled drawing. When we see sunlight emanating from this center of our universe towards the Earth, and pardon my sort of wiggly line there, it strikes the Earth someplace south of the equator during the southern hemisphere's spring to fall. And the direct sunlight is the most intense, has the most energy. You can see also that there is light up here hitting the Earth, but I'll show you in a later slide that it's a different angle of incidence. So let's look at this. This is a little thought experiment. We have two flashlights. One is at a 90-degree angle to the table, and one is at a much lower angle relative to the table. So I want to ask you to just in the back of your mind, or maybe on a sheet of paper, jot down a note or two. Which one of those shines more brightly? That is, which one has a greater intensity? What is the light going to look like when it hits the table? And then why do you think so? So you may want to pause the video here and just jot down a note or two. Do me a favor and also sketch this for your notes. So looking at flashlight A, we can see that it's shining at a 90-degree angle to the table, more or less, and it's making a small spot of intense light. What happens with B? What do you think is going to happen? What will that spot look like? It illuminates a larger area, but it's not as intense. It's dimmer. So we see a very bright yellow here compared with sort of the pale yellow here. The same is true. This functions in a very similar way as sunlight strikes the Earth. The higher the angle, the more intense the light on the surface of the planet. So when we look at this is a figure 223 from your textbook. This is showing you the same thing. Here is the first flashlight shining directly at 90 degrees or orthogonally to the surface of the Earth. And here is the same light source hitting at a point higher up on the sphere of the Earth. So sunlight, we imagine the sun being a great big object over here, and we probably could barely even get its curvature shown in here. But if this is the center of the sun, we don't see much difference in the angle of the direct sunlight around throughout the course of the year. But the location where that intense bright circle is located does change throughout the year. So as the planet revolves around the sun, we're going to see 4 major seasonal events that happen with respect to sunlight on the planet. What's going to happen over the seasons is that the intensity of sunlight is going to change, right? That happens everywhere. The intensity of the sunlight changes, as does the duration of the sunlight. And so we have very long days in the summertime. Here is the June 21st seasonal event. And you can see the direct sunlight is striking the Tropic of Cancer, so the northern tropic line. And you'll notice here that that tropic is at 23.5 degrees north, the same angle as the Earth's axis makes with the circle of illumination. Okay, so those two angles are the same. Let's go on to the next slide here. The angle, sometimes called the altitude of the sun above the horizon, affects the amount of solar energy that reaches the Earth's surface. When the sun is directly overhead at a 90-degree angle, the solar rays are most concentrated and thus most intense. At lower sun angles, the rays become more spread out and less intense. This explains why tropical areas, like the area here, experience a consistent higher sun angles throughout the year have a much higher temperature than the polar regions, where the sun angles are much lower. So here's a polar region. The angle at which the sun strikes a particular location varies seasonally because the Earth is also revolving. For example, someone living in Chicago, the sun is highest in the sky at noon on June 21st. When comparing seasonal changes in sun angles, noon solar time is used because that's when the sun is at the highest point in the sky. But as summer gives way to autumn, the noon sun gradually appears lower in the sky from one day to the next, and sunset occurs earlier and earlier each evening. The lowest sun angle and earliest sunset in Chicago occurs on December 21st. What causes, this is, I guess, the question here. What causes fluctuations in the sun angle and length of daylight during the course of the year? To figure that out, we have to look at the model that shows us rotation and revolution. And I like the one that I'm showing here. It's not in your textbook, but it's a different one. And by looking at this one, you'll have access to both. The good one and the one that I think is not quite as good that's in your textbook. But Earth's axis is not perpendicular to the plane of its orbit around the sun. This plane, right, the one that's encircled by these blue arrows, is called the plane of the ecliptic. It's tilted at about 23.5 degrees away from the plane of the ecliptic. Here we can see, here's the circle of illumination, right? The COI, and it is perpendicular to the plane of the ecliptic. So the poles are also tipped 23.5 degrees from the circle of illumination because the equator is perpendicular to the geographic north and south poles. If the axis weren't inclined, we wouldn't have any seasons. Because the axis is always pointed in the same direction, that's another thing. Look, it's pointing this way in this picture, this way in this picture, this way in this picture, and this way in this picture, right? The direction that the axis points is the same throughout the year. Okay, and because that's true, the orientation of the axis to the sun's rays is always changing. For example, on one day in June each year, Earth's position in orbit is such that the northern hemisphere is leaning 23.5 degrees towards the sun. Towards the sun, right? This is our summer solstice. 6 months later in December, over here on the right-hand side, when the Earth has moved to the opposite side of the orbit, the northern hemisphere sort of leans away from the sun, but also at 23.5 degrees angle. On days between these two extremes, Earth's axis leans at amounts less than 23.5 degrees relative to the rays of the sun. So the change in orientation of the planet causes the spot where the sun's rays are vertical to make an annual migration from the tropic in the northern hemisphere to the tropic in the southern hemisphere. So here we see that point, perpendicular sunlight, hitting the southern tropic, the Tropic of Capricorn. And here during our summer, the sunlight is hitting the Tropic of Cancer in the northern hemisphere. Both of those tropics lie at 23.5 degrees latitude. Cancer is in the north. I remember that because the word Cancer has an N in the middle of it, and Capricorn doesn't. For all mid-latitudes during that year, the migration causes the angle of the noon sun to vary. A city like New York, for example, has a maximum noon sun angle of about 73.5 degrees when the sun's vertical rays have reached their farthest northward location. That's, in other words, not 90. The sun isn't directly overhead, right? The sun can only be directly overhead if we're somewhere between the two tropics. 6 months later, the New York City will have a minimum noon sun angle of 26.5 degrees. By contrast, a city on the equator will experience an annual migration of only 23.5 degrees. These are, I'm talking a lot about the measurements. I don't think I'm going to ask you guys to calculate the noon sun angle at a specific location. But your next weather class, you might do that. Based on the annual migration of the direct rays of the sun, 4 days out of each year are especially significant. On June 21st or 22nd, the vertical rays of the sun strike 23.5 degrees north latitude. That's 23.5 degrees north of the equator. That line of latitude is the Tropic of Cancer, and for people living in the northern hemisphere, June 21st is the official summer solstice, or the first official day of summer. 6 months later, on December 21st, Earth leans in the opposite direction, so the sun's vertical rays strike at 23.5 degrees south latitude. The line of latitude located at 23.5 degrees south is the Tropic of Capricorn. For those people in the northern hemisphere, which includes us, December 21st is the winter solstice, the first day of winter. However, on the same day, people in the southern hemisphere experience their summer solstice. The equinoxes occur midway between the two solstices, and that's the picture shown down here in figure C. The equinoxes are days when the vertical rays of the sun strike the equator, 0 degrees latitude, because Earth's position is such that its axis is tilted neither towards nor away from the sun. If we go back, let's see if I can do this. I can't go backwards in this video. But if you go back and look at the picture of the Earth rotating around the sun, the revolution diagram, you'll see that on the dates of the equinoxes, the north hemisphere sort of tilts towards the direction it's going or away from the direction the planet's going, based on which time of year it is. So the length of daylight on the summer solstice in the northern hemisphere, June 21st, is greater than the length of night. That fact can be established by examining figure 2.6, which is this one I have in here. The circle of illumination is that boundary that separates the dark half of the Earth from the light half. The length of daylight is established by comparing the fraction of a line of latitude that is on the day side of the circle with the fraction that's on the night side of the circle. Okay, so here we can see 23.5 degrees. This is our December solstice. You can see the length of day is only 10.5 hours. Okay, so a smaller portion of this 23.5 degree line is illuminated compared to the fraction on the night side, which is not illuminated. So the length of this yellow line is greater than the length of that red line. And if you look at the summer months, here we see a daylight out of 24 total hours. The southern Tropic of Capricorn, has a shorter length of the 23.5 line than does the illuminated length. So this is a long day and a short night. Here's another view. I'm very critical of the version of this figure that's in your textbook because it's actually not meant to be a one-dimensional picture. It's meant to be an animation. And when you're looking at the textbook, you don't benefit from that animation. This comes from a different textbook by Tarbuck and Lutkins, and I like this version of the picture better. Note on the table 2.1, that lists the length of day for different latitudes. The further north a location is from the equator on June 21st, the longer the period of daylight. When you reach the Arctic Circle at 66.5 degrees north latitude, the length of daylight is 24 hours. Places located on or north of the Arctic Circle experience the midnight sun, which means the sun doesn't set for a period that ranges from 1 day at the Arctic Circle to about 6 months at the poles. The seasonal changes in length of day and intensity of sunlight are the primary causes of the month-to-month variations in temperatures observed at most locations outside the tropics. In this figure, the three different pictures illustrate the daily pass of the sun for a location at 40 degrees north latitude for the seasons of the year. So notice that the length of daylight is longest and the sun angle is highest in the sky during the summer solstice. Okay? While the opposite is true for the winter solstice. Okay, here's the opposite. If you look at the fourth, the extra corner of this figure, you can see the path of the midnight sun for a location at 80 degrees north. So with figure A, the summer solstice, day length and the sun angle are maximized. So this is the hot season. Okay, we have a lot of energy coming in directly from the sun at a very high angle, and the day lasts a long time, so the Earth stores up a lot more heat. Between that summer solstice and the winter solstice, we'll go through an equinox, right? And this is the time when the yellow band, the length of the 40-degree north latitude line that's illuminated is as long as the one that is not illuminated. So summer solstice, then comes spring solstice, and we know the daylight lasts 12 hours and the nighttime lasts 12 hours. So equi is equal, nox, night. The night is equal to the day. Then 3 months after this false equinox, we'll get to figure C, which is the winter solstice. And this is a very unique location. It's a unique location because there's no change in the vegetation cover with the seasons. Wouldn't it be nice if we saw multicolored leaves on the trees and maybe the grass get a little bit browner here? But here is the winter solstice, the first day of winter. And at this point in our calendar, the day length and the sun angle are at their minimum. So this is wrong. That should say minimum. Okay. That's just one of my little mistakes here. So during a summer solstice, these two happen at roughly the same, well, not exactly, let's say exactly the same time. That is the path of the midnight sun. You'll see the sun get as low as just above the horizon at midnight, and at noon it'll be at its highest point above the horizon, but it still won't be as high as the sun angle is here in the mid-latitude. So you'll see a sun angle of a maximum of 33.5 degrees if we're at 80 degrees north, and at a maximum of 50 if we're here at 90. Do you notice something about these numbers? Here we're at 40 degrees north, okay? And if we add 50 degrees, the sun angle, to 40, we get 90, right? And that's the total number of degrees between the equator and the pole. So what happens if we're at 80 degrees, right? And we compare that latitude with this one. If we take away 10 degrees, right, from 90, we are at 80 degrees latitude. If we take 10 degrees away from, or if we add those 10 degrees onto the 23.5 degrees, the tilt of the axis, where are we? At 90 degrees. So this table sort of summarizes the characteristics of the solstices and equinox. This is the material that I would study the most for learning seasonal differences. Okay, try not just to blindly remember them as rote, but remember them in terms of one of your, whichever figure kind of shakes things loose for you. So imagine these dates, the angle of incidence, the length of daylight at the different solstices and equinoxes throughout the year. And we'll work on this a little bit in lab this week. Looking at the information from the previous figure, which is up here at the top, you should be able to understand why mid-latitude locations are warmest in the summer, the days are longest, and the angle of the sun above the horizon is the highest. The winter solstice facts are the reverse. The days are shortest, the sun angle is lowest. So during an equinox, which again means equal night, so day and length of daylight is 12 hours everywhere. And so is the day of the length of night. All locations situated at the same latitude have identical sun angles and lengths of daylight. If the Earth-Sun relationships were the only controls of temperature, we would expect those places to have identical temperatures as well. Obviously, that's not the case. Although the angle of the sun above the horizon and the length of daylight are the primary controls of temperature, other factors have to be considered too. So seasonal fluctuations in the amount of solar energy reaching various places on Earth's surface are caused by the migrating vertical rays of the sun and the resulting variations in sun angle and length of daylight. Because the weather phenomena we normally associate with each season don't coincide well with the astronomical seasons, meteorologists and climatologists prefer to divide the year into 4 3-month periods, into quarters basically, based primarily on temperature. So winter is defined as December, January, and February. Okay? The 3 coldest months of the year in the Northern Hemisphere. Summer is defined as the 3 warmest months, June, July, and August. Spring and autumn are the transition periods between those 2 seasons, inasmuch as these 4 3-month periods better reflect the temperatures and weather that we associate with the respective climatological seasons. That definition of the seasons is more useful for meteorology. Use the course content provided on the Canvas site as well as outside sources to verify that you can formulate answers to these questions. If you can comfortably answer these questions, you're in great shape. If you can't, review the textbook, rewatch the video, see if your abilities improve. If you're still completely stumped, start a discussion on the Canvas site or ask me for help. I will happily answer.